Now, welcome to the next class. So, in this present class, we will try to understand what is that overall balances are also called macroscopic balances. So, this will be our 12th class on the transport phenomena, TP12. Overall, or it is also called macroscopic balance. Till today, we have gone through the differential balances, differential mass balance or the equation of continuity, differential momentum balance, that is the equation of motion. So far the energy balance is considered, I am leaving that differential energy balance for the present moment, because there are many things which cannot be dealt at the present moment of time, but that I will definitely deal later on in the classes of this subject, the transport phenomena. So, prior to that, we will start to learn what is this overall balance or macroscopic balance. During the derivation of this macroscopic balance, you have gone through the aspect that during the flow of the fluid, generally we consider a differential volume of quarter minus edge length delta x, delta y, delta z along the three mutually perpendicular Cartesian coordinate axes. These equations can be extended to the spherical polar coordinates and the cylindrical polar coordinates as well along the r theta phi direction and r theta z direction respectively in aforesaid coordinate system, and the corresponding the differential balance equation can be obtained in that case as well. Now, the question arises, if we have gone through these macroscopic balances, why there is necessity to go for the overall macroscopic balance? So far as the result obtained from the macroscopic balances are concerned, it is very much accurate in nature, but at the very same time the fallacy is it requires complex mathematical steps therein. The concepts of vector calculus, the concept of combining the equation for all these three coordinate systems by utilizing the vector calculus parameters are creating sometimes problems for a practicing engineer. Also, this approach, those approaches are very much analytical in nature, and that is why they have produced the strong and concrete results. Now, the question arises, why there is necessity of overall or macroscopic balances? I am giving you the points on the basis of which you can easily decide why the macroscopic balances are required over the macroscopic balance. So, if I am asking why macroscopic balances, are required, then the answer is number one, macroscopic balance formalism requires a little complex mathematical tools to arrive at results amenable to a practical situation. Why I am writing this statement? I am writing this statement on the basis of the fact that even though the differential balance or macroscopic balances are creating very concrete results, but those concrete results are necessity for a mathematician, not for a necessity of an engineer. An engineer requires many times approximate data. Let us suppose you are operating a blast furnace and you have to decide the time in which the slag can be completely removed from the blast furnace. Knowing the dimension of the slag nozzle or slag notch, if you start applying the differential balances in those cases, so it is very cumbersome to take a fluid element as the slag is flowing at a higher temperature from the blast furnace to the atmosphere. So it creates a very cumbersome situation for a practicing engineer to execute. However, by adopting the common principle of the macroscopic or overall balances, it is possible to arrive at the time required for the complete cleaning of the slag from the blast furnace. You can use the inlet and outlet conditions only, that is the condition inside the blast furnace, and conditions at the point from which the slag is going to disappear from the blast furnace to the atmosphere in the ladle. You can determine the approximate time for the doing this practice. So even the results are not so much accurate in nature, but still it has much importance for a practicing engineer. That is why the macroscopic balance formalisms are required. Number 2, specific and accurate boundary conditions may not be required in cases of macroscopic or overall balances. The boundary conditions we have encountered in the differential balance, those are very accurate in nature, because of the fact that geometry is accurate. You are taking a rectangular parallelopipe, you are taking a cuboid, this much edge length. That means if I am taking the delta x equal to delta x, it means the delta x ends at the same point, the point which has been shown on the diagram for that point lying on that cuboid or the parallelopipe. Such type of accuracy in the boundary condition is very difficult so far as the practical engineering problems are concerned. So this is the second advantage associated with this macroscopic balance. So that is why it is regarded as a useful mean for the practicing engineer. So third thing is the microscopic balance. I am talking about microscopic balance. Microscopic balance is valid for laminar flows and regular geometries only. In the cases of practical problems, neither a full laminar flow nor a regular geometry is possible, because in the practical problems you don't know that whether the slag during the entire course of its detachment from the blast furnace will follow the laminar flow. For executing a laminar flow, depending upon the density of the liquid, the velocity of the liquid, the dynamic viscosity of the liquid, all these parameters may change as per the conditions at the inlet and outlet, because at the inlet, that is inside the blast furnace, the slag may be at higher temperature. Once it is exposed to atmosphere, the slight change in temperature is there from 1600 or 1700 degrees centigrade to the room temperature. Correspondingly, the viscosity will get changed. So, neither a full laminar flow nor a regular geometry is possible in the case of the practical problem. Let us take the example of the slag notch. If any quantity of slag will get solidified over the inside wall of the slag notch, a proper geometry can never be followed. In the viewpoint of all these 3 points stated by me in the class, that can easily explain that why microscopic balances are required over the macroscopic balance. So, this microscopic balance it is an approach. Now I am coming the full-fledged discussion of this macroscopic balance. It is an approach based on the inlet and outlet conditions of a system, which may not require complex mathematics. The results obtained from such approaches are approximate in nature, however, of immense importance, so far as practical engineering problems example flow of liquid metal through the inlets and the risers, through the, or you can say through the gating and rising system, in a particular solidification process, in a particular solidification problem. Number 2, flow of liquid steel from a teaming ladle, from a ladle or teaming ladle etc. are concerned. I will provide you the flavor of such things by giving an example at the end of this class, that how the concept of this overall balance can be utilized in the case of the ladle, in order to evaluate the time required for inputting of a ladle, inputting of a teaming ladle. So, let us consider the overall mass balance now. Let us consider the overall mass balance. Let us consider the overall or macroscopic, MACRO, macroscopic mass balance. In order to have the flavor of this overall or macroscopic mass balance, let us consider a reactor. Let us consider a reactor. I am assuming a reactor of the volume VR. This is the center line of your reactor. This is the center line of your reactor. So, the fluid is entering, this is the entry point, and at the exit point the fluid is leaving this reactor. Okay. I am assuming a reactor of volume capital V R. For mass balance formalism. So, as shown in the figure, let us suppose the fluid is entering at this point with the velocity v e and the density is rho e, and it is leaving at this point. Let us suppose this is v exit, velocity of at exit point and density at exit point. So, as shown in the figure, there is a reactor of volume VR AE and AEX are the cross sectional areas of the reactor at entry and exit points respectively, at entry and exit points respectively. Applying the principle of conservation of mass, applying the principle of conservation of mass, because as I have taught you that the differential mass balance is the equation of continuity, and that is based on the principle of conservation of mass. On the same guideline, the overall mass balance is also based on the principle of conservation of mass and also the equation of continuity as well. Applying the principle of conservation of mass for the present reactor, we can write amount of fluid entering the reactor per unit time minus amount of fluid leaving the reactor per unit time that should be equal to amount of fluid reacted inside the reactor is it not? Because the quantity of fluid which is entering the reactor, so one or two fluid or three fluids may be there, or even in the case of the single fluid also, there are chances that that fluid may react with the reactor wall, and form some product. Many products may be of the nature that if the product is gaseous in nature, then the product may leave the reactor, or they may get entrapped within the reactor. So, in order to have a complete mass balance in this case, we can say the amount of fluid entering into the reactor per unit time minus amount of fluid leaving the reactor per unit time, so in minus out, that should be equal to amount of fluid reacted in the reactor and the remaining this plus amount of fluid retained in the reactor. So, the amount of fluid reacted in the inside the reactor plus amount of fluid retained in the reactor. So, this is the basic equation for the mass balance formalism. Let us try to evaluate all these four quantities, and putting in the equation number 1, we will get the overall equation corresponding to the overall mass balance formalism. So, the amount of fluid entering the reactor per unit time that should be equal to rho E into V E into A E. How? You can check with this equation dimensionally. Rho E V E A E, the dimension is m L raised to the power minus 3, velocity L t to the power minus 1, area is L square. So, L square L cube cancel out, that is equal to m t to the power minus 1, that is equal to m upon t, that is the mass, amount of fluid entering per unit time. So, the amount of fluid entering per unit time, that is the rho E V E into A E. Similarly, amount of fluid leaving the reactor per unit time, that should be equal to density at exit, velocity of exit and the area at exit. Let it be question number 3. If RF is the amount of fluid reacted inside the reactor per unit time per unit volume, if I am assuming that the RF is the amount of fluid reacted inside the reactor per unit time per unit volume, then the amount of fluid reacted, then amount of fluid reacted inside the reactor that should be equal to how much? Volume of the reactor into RF, that is equal to VR into RF. Let it be question number 4. Now, day bar rho by day bar t, the rate of change of density, of fluid, assuming its compressible nature, So, the amount of fluid retained in the reactor, that is equal to VR into day bar rho by day bar t. Let it be question number 5. Now, from equation number 1 to 5, that means putting equation number 2 to 5 in 1. Putting equations 2 to 5 in one, we get rho E V E A E minus rho E x V E x A E x, that should be equal to V R R F plus V R d rho upon dt, or you can write rho E V E A E minus rho E x V E x A E x, that is equal to V R R F plus d bar rho by d bar t, or you can say it minus increase into the rho V and A value, because of the fact that if the fluid is flowing from the entry to exit point, that means this quantity is more as compared to this quantity. So, that is why a negative sign has been used here. So, minus delta into rho V A, that is equal to V R R F plus d bar rho by d bar t, or V R R F plus d bar rho by d bar t plus delta rho V A, that is equal to 0. Let it be question number 6, let it be question number 7. This quantity is the difference in mass flow rates, because I have told you earlier that this dimension is m upon t, that is the quantity of mass entering or leaving the reactor per unit time, that is the mass flow rate. So, the difference in mass flow rates at entry and exit points and equation number 7 is regarded as a differential form of equation number 6, and this is called your mass balance formula. Now, if a system has so many components, then equation number 7 can be made applicable to a differential length along the flow direction, considering the entire cross section of the reactor, cross section of the reactor. this principle of overall mass balance, this principle of overall mass balance can be effectively used in modeling of blast furnace, can be effectively used for the modeling of blast furnace, can be used in modeling of blast furnace, shaft furnace, calcination furnace. So, you can easily deduce the fact that this overall mass balance formalism is of immense importance for a metallurgist, so far as the designing of all the processes related to the blast furnace, related with the production of iron in the low shaft furnace, as well as the calcination process for the various carbonates and the bicarbonates of the metals in the non-ferrous extraction metallurgy. Now, I am establishing this overall mass balance formalism by giving an example in the form of a numerical problem. So, let us try to have the flavor of this overall mass balance formalism through an example. I will take an example of a teaming ladle and try to arrive at the expression for the time required for the complete emptying a ladle of liquid steel. So, this illustration of this overall mass balance formalism, illustration to develop an expression for time required for inputting a ladle containing liquid steel of volume VR. There is a nozzle, situated at the bottom of the ladle. So, let us suppose this is a practical problem that you have as a practicing engineer. My main emphasis to illustrate this example, that how can you obtain an expression for the time for inputting a ladle, from where you can easily put the value of the required variables therein to arrive at the approximate time for the inputting a ladle. So, let us proceed in this problem by taking the help of this overall mass balance formalism. Since the derivation, since no steel enters the ladle, because you have taken the bulk of the liquid steel in the ladle at the initial stage, After that, you are not pouring any liquid steel in that ladle. So, no steel enters the ladles, plus nothing is reacting inside the ladle. It implies that Rf is equal to 0. It implies that Rf is equal to 0. Hence, applying the overall mass balance formalism for the case, mass balance formalism for the case, we can write that rho E V E A E minus rho E x V E x A E x, that should be equal to V R R F plus V R d rho upon dt. Nothing is entering, so this quantity is 0. Nothing is entering, so this quantity is equal to 0. Nothing is reacting, so this quantity is also 0. So, you can write minus rho E x V E x A E x, that is equal to V R d rho upon dt. Instead of this V R d rho by dt, we can write here the quantity of amount which is retained in the reactor per unit time deba by deba t into the volume of the steel V R into rho dm by dt, that is the quantity of mass retained. So, this quantity can be written as V R d rho by dt plus rho d V R upon dt. Now, in this quantity you can easily see, if I am assuming the incompressible nature of the steel, then this quantity also tends to 0, and in this quantity rho is taken as a constant quantity because it is incompressible nature. So, rho does not change. The quantity which is changing, that is the quantity of the steel, is changing all the time, because there is a continuous removal of the ladle from continuous removal of the steel from the ladle to the atmosphere is going on through the nozzle at the bottom. This quantity is 0. So, we can write minus rho E x V E x A E x, that should be equal to rho deva V R by deva t. So, also rho E x, that should be equal to rho incompressible nature, incompressible steel I am assuming. So, this quantity also will get cancelled out. So, minus V x into A E x, that is equal to d V R by dt. This partial derivative is only a function of t. So, it can be written as d V R upon dt, that should be equal to minus V E x A E x, or d V R, that is equal to minus V E x A E x into dt, integrating initial at time t is equal to 0, what is the volume? Vr is equal to Vr. At time t is equal to t, when the inputting of the ladle is executed fully, so t is equal to t, that is the Vr is equal to 0. So we can write here minus Vr, that should be equal to minus small Vex Aex into t. So thus the expression for t, that is the time required for inputting of ladle, so the time required for inputting of ladle, inputting the ladle is given as t is equal to Vr divided by Vex Aex. This is the expression for the time. This equation can be further solved if d is the diameter of nozzle. So the nozzle is regarded as the exit point. So then Aex is equal to pi d square by 4. Okay. Hence, expression for t is equal to Vr divided by Vex into pi d square into 4. So the expression for this comes as 4Vr divided by pi into Vex d square, that will be equal to pi 4 divided by 3.14. This will come as 1.274 Vr divided by Vex into d square. This is the required expression for time required. Required expression for time required for inputting the ladle. This is the illustration. This is a simple illustration that I have shown you in order to have the understanding of this overall mass balance formalism. In the next class, we will discuss the overall momentum balance formalism. Thank you.